Our conventional physics teaches us that there are four fundamental forces at work in the universe: the strong force, the weak force, the electromagnetic force, and the gravitational force. They work over different ranges and have different strengths, and are the reason behind most of the universe's function as we know it. From playing basketball to launching a rocket into space to sticking a magnet on your refrigerator, all the forces that all of us experience every day can be whittled down to this critical quartet. Yet there are a lot of explanations missing. We still have no idea what dark energy is and how it's expanding the universe, or what exactly dark matter is made of, among many other mysteries of deep space that our knowledge of physics is perhaps too limited to understand. Welcome to Factnominal, and today let's look at the discovery of the fifth force of nature that we're quite sure exists, but don't comprehend entirely yet. In one of our recent videos about data collected by the Hubble telescope, we talked about how there's something missing out there, a source of energy, or perhaps a force that's messing with the Hubble constant, the rate at which the universe expands. However, there's a problem when we try to understand this phenomenon. We don't possess the right knowledge to analyze this power. Our physics is incomplete. We may have to change a lot of things about what we know as universal physics to understand what we don't yet know, and that can be scary for a lot of people. A new study that's grounded in the research of dark matter is proposing something similar, and that can be both daunting and equally fascinating. The researchers from the University of Nottingham found that their new study could lead toward a first potential new physics explanation that's still based on dark matter. In contrast to previous studies, this recent study suggests that hypothetical particles, called symmetrons, are generating invisible walls in space that hold galaxies in their orbits. But what the heck are symmetrons in the first place? For years, scientists have been trying to understand dark matter and dark energy from the perspective of our current inventory of particles and forces in nature, but they simply aren't able to explain major cosmological phenomena, such as why the universe is expanding at an ever faster rate, or what holds galaxies' shapes together. Interestingly, both of these phenomena are somewhat related. One of the candidates for explanation is the so-called symmetron field, which is said to pervade space much like the Higgs field. The Higgs field is a theoretical field of energy that exists in every region of the universe. The field is accompanied by a fundamental particle known as the Higgs boson, aka the God particle, which is used by the field to continuously interact with other particles, such as the electron. While the Higgs boson provides mass to every particle that enters its field, symmetrons are supposed to provide shape to everything that interacts with it, such as galaxies. However, it's too early to call for that, as researchers believe that there's still a 50-50 chance that they could be wrong. However, it is a step towards understanding that mysterious isle of astrophysics that we don't understand whatsoever. In order to prove that there are indeed invisible walls in space, the burden that symmetrons exist must be fulfilled first. Space instruments like the James Webb Telescope and others could be beneficial in this possible endeavor as they study how the universe was formed in its early stages. And to tackle this challenge, we must come up with a solution for the satellite disk problem. The lambda cold dark matter model is currently considered the standard model for understanding the positions of galaxies around each other, but it has its issues. The lambda model presupposes that small galaxies should be scattered in messy orbits around larger galaxies, but the majority of the small galaxies orbiting their large counterparts are arrayed in thin, flat planes. Interestingly, these disks or planes are strikingly similar to the rings of Saturn, which kind of makes it look like there's an invisible wall in space that sets these galaxies into an arranged order. Astronomers often refer to these walls as satellites, which can be located in synced-up orbits all over our galaxy, and they've observed them in neighboring galaxies as well. Over the past few years, experts have proposed several explanations that could solve the satellite disk problem. However, as with the Higgs particle, whose mass wasn't known until the existence of the particle was confirmed, the physical properties of symmetrons cannot be accurately predicted. Unlike the Higgs boson, whose existence was proved by experiments performed here on Earth, symmetrons are a little bit trickier in that regard. Nobody can say what the mass of a symmetron is, nor how strongly they interact with normal matter, and that's what makes them a kind of Schrodinger's cat. It's hard to prove if they exist or not, and there's no way to open the box. So, what can we do? Maybe understanding the other four forces may hold a clue. In no particular order, as we mentioned earlier, the four forces of nature that govern the observable universe are gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. Gravity is obviously the easiest to understand and explain. Ask Newton. He got hit on the head by an apple, and that actually helped. Okay, maybe that story isn't entirely true, but we do know that an apple was involved. Gravity is the force that causes any two things that have mass, such as atoms, people, planets, stars, etc., to draw towards each other. The bigger the mass, the stronger the pull. Easy peasy. But that doesn't exactly work in my case, though. I'm quite buff, and it doesn't seem to magically draw women to me. Anyway, on to the next one. The next one is also not that tough to explain. To be honest, it's quite self-explanatory by its name, electromagnetism. That's just electricity and magnetism mixed together. Well, actually, there's a bit more to it than that. The electromagnetic force explains how things that are electrically charged, positively or negatively, interact with each other. One of the major understandings is that a magnetic charge can create an electric charge and vice versa. Those interactions are responsible for electric power generation, which is kind of a big deal. Electromagnetism and how it pushes and pulls objects is responsible for the energy in things like batteries and magnets, but it also includes light, which is just waves of electromagnetic radiation. The last two, the strong and weak forces, are theoretically stronger than gravity, but they work at the micro level only. That is, at very short distances. That means in the tiny spaces between atoms, and the even smaller spaces where quantum physics starts making everything really weird. That's why they're called the strong and weak nuclear forces. In fact, the strong nuclear force is the strongest of the four known forces, and is basically the glue that binds everything together. It's responsible for keeping protons and neutrons stable, and then allows them to join and become atomic nuclei. The weak force, the opposite of the strong force, on the other hand, is responsible for radioactive decay. It's what controls how things on a nuclear level fall apart. And also, before we forget to mention it, the weak nuclear force is also responsible for fusion and keeps our lovely sun all bright and warm-like. Not really that weak in its function, is it? However, while we did explain what these four forces are or do, we didn't talk about what makes them tick, why they act the way they do, and what's the reason behind their existence. Does one body with mass just magically start moving towards another massive thing? No. If that was the case, I wouldn't be having such a hard time finding a date. But in all seriousness, it's made possible by things called force carrier particles. Force carriers are the particles that carry information between things and tell them how to behave. Think of force carriers as little pocket constitutions for each of the four fundamental forces. They lay out not only all the rules for how to behave, but also force the forces to act by those rules. You can call them one force to force them all, or the forcest force to ever force. The force carriers for gravity are hypothetical things called gravitons. For electromagnetism, they're photons. For the weak nuclear force, the carriers are called W and Z particles, and for the strong nuclear force, gluons. These force carriers are all classified as kinds of bosons. And now we're close to the possibility of throwing symmetrons into the mix as well, if the hypothesis proffered by the team from the University of Nottingham bears fruit. If symmetrons exist, that means a force that's carried by them must exist as well. In 2015, a group of physicists at the Hungarian Academy of Sciences saw what the University of California at Irvine Physics department called puzzling anomalies in their experimental data. The Hungarians weren't sure what the anomalies were, but they pointed to the existence of a new kind of light particle. However, that's where the lead stopped, as the Hungarians were unable to calculate if this particle had a mass or not, as is the case with photons. Later, a professor of physics at the University of California at Irvine, one Jonathan Fang, christened this particle the X boson, at least for the time being. It's believed that the force carried by the X boson is very similar to electromagnetism. However, while the normal electric force acts on electrons and protons, this newfound boson interacts only with electrons and neutrons, and at an extremely limited range. Frustratingly, that's all we know about the X boson as the candidate for the carrier particle of this particular brand of the speculated fifth force. On the other hand, a new study from the University of Nottingham presents a fresher explanation of symmetrons that constitute the buildup of space walls between and around galaxies. This could possibly solve this long-standing mystery once and for all. However, further details regarding this study have yet to be made public, so we'll have to wait a little longer for the really juicy bits. But for now, the future's looking brighter. Who knows how this knowledge may revolutionize our understanding of the universe and what we would be able to achieve with it. Tell us in the comments, do you think could there be a sixth, a seventh, or even possibly more forces of nature that are yet to be discovered? And as always, thanks for watching Factnominal. Don't forget to like, share, and subscribe.